Hello students, welcome to Vyas Edification Kota. In this series of NCERT discussion, we'll continue further with Mathematics class 12th. The chapter that we're dealing with is integrals, and now is the turn of exercise 7.5. Now this particular exercise is based on an important method of integration, which is called integration using partial fractions. Now for some questions which are algebraic, let us say algebraic functions, so how do we integrate those algebraic functions? Furthermore, some functions which can be converted into algebraic functions, and how do we integrate those particular functions, right? In particular, we'll be talking about rational functions over here. Now what kind of a rational functions are we talking about? Something related to polynomial upon polynomial. This is what you look at, polynomial upon polynomial, and in that also the degree of numerator and degree of denominator. We should be looking forward to solving degree of numerator is lesser than degree of denominator. Now in case that is called a proper rational function right now. So in case you get a degree greater in the numerator, what do? You use a long division and you divide the numerator with the denominator. You get some quotient and you get some remainder. So remainder will come on the top, the quotient will be left on the side, and obviously the degree of remainder will be less than the degree of denominator. So that particular rational function, proper rational function, is what will be learning to integrate in this particular exercise along with the questions one by one, right? So in the method, the first and foremost important thing is to convert any proper rational function as sum of partial fractions, right? To write it as sum of different fractions. The fractions in themselves will be easily integrable. That's what we are looking forward to, right? So along with the questions, we'll be seeing the method to convert into partial fractions, and then we'll be integrating those partial fractions, right? So one by one, let's move on to the questions. First question says that integrate the rational functions in exercises 1 to 21. Okay, so the first one begins with x upon x plus 1 times x plus 2. How do we handle this? So the first thing that we are supposed to do is, okay, we have x upon x plus 1, x plus 2. So let's begin with this, x upon x plus 1, x plus 2. This is similar to, this has two linear factors in the denominator, right? And degree of numerator is less than degree of denominator. Those two things have been checked, right? The denominator is factorized and the degree of numerator is less than degree of denominator. If these two things are there, then we can move to the next step, right? So first step, is the degree less? Yes. Second, is the denominator factorized? Yes. Okay. So first, degree of numerator is less than degree of denominator. This is important, right? If that will not be the case, then you'll have to use long division and divide first. Second, factorization of denominator into linear and quadratic factors. Right? This is important. Denominator has to be factorized into linear and quadratic factors. In that case, we'll be dealing with this particular method, right? And after that, we'll be converting into partial fractions. And then integrate. Right? So how do we convert into partial fractions? The conversion into partial fractions involve these few steps. What are the steps, right? You write it as a separate term for x plus 1 and a separate term for x plus 2, and you actually write it as a upon x plus 1, some coefficient with x plus 1 and some coefficient with x plus 2. Target is to find the values of a and b now, and such that this is always equal to this. Okay, target will be to find a and b such that this is always equal to this, implies that this is an identity over here. And how do we deal with that? So there are some shortcuts, yes there are, but other than that, when we take a look at this, what do we say? Okay, let's write it as, let's simplify this over here, and to find the values of a and b, we are writing it as this, and this tells me, okay, a times x plus 2 plus b times x plus 1 is there in the numerator. Okay, if the denominators are equal, therefore the numerators have to be equal, x equal to a plus b times x. Do you observe the numerator over here on the right hand side? Yes, ax bx will be a plus bx, 2a plus b will be extra. This is 2a plus b extra, right? And by simple comparison, since this is always equal to this, by simple comparison, what do you say? that a plus b, this coefficient of x over here should be equal to coefficient of x over there. This is equal to 1. And moreover, this 2a plus b, this 2a plus b over here has to be 0, as you see over there. There is no constant term. This constant term has to be 0, right or not? Yes. Okay, let's subtract these two, and what do we get? 2a minus a will give me a, b minus b is gone, is equal to minus 1. And b is equal to 1 plus 1, 2. This is what you get, right? This is what you get. So a is equal to minus 1, b is equal to 2. This is something which I have obtained. Therefore, we can say, therefore, I, the integral of x upon x plus 1 times x plus 2 dx is actually equal to integral of a, which is minus 1 upon x plus 1, minus 1 upon x plus 1 plus 2 upon x plus 2 integral of this particular expression. Now take a look at this. This should be always equal to this. Yes, this is an identity kind of thing. Yes. And let's simplify this. This is minus x minus 2 plus x plus 2, right? Sorry, plus 2x plus 2. So minus 2 and plus 2 will get cancelled. 2x minus x will be actually x in the numerator. This is always equal to this, which you can see by simplification also. And that is how we have actually calculated the values of a and b. Okay. And once we reach this stage, do you realize that integration of this and integration of this is very, very simple? Yes. And that's the key. So this is minus integral of dx upon x plus 1 plus 2 times integral of dx upon x plus 2. This is what you have. And this becomes, the integral becomes log modulus x plus 1. There's a minus over here, right? For x plus 1, the coefficient of x is simply 1. So that will come in the denominator. That's not important. Plus 2 times log modulus x plus 2 plus constant term. This is what you get, right? So you can leave the answer at this stage, minus of this plus 2 times log of this, or you can combine the two logs, and write it as, okay, this 2 will go over here in the power log of x plus 2 square and minus of log x plus 1. So this will become log of x plus 2 square upon x plus 1 and its modulus. This is the expression within the log plus constant term. This or this, any of these forms are okay, right? So that's the final answer for this particular question. As you can see over here in this question, the steps, mind you, first observation over here works because degree of numerator is less than degree of denominator. That's just something should be there for a proper rational function. Denominator should be factorized into linear and quadratic factors, and after that we convert into partial fractions using those steps. Then we integrate easily. Right? That's the complete solution of this first question, as you can see over here. Second question says integrate 1 upon x square minus 9. Now, how do we deal with this? Once again, the first important thing to note here is the degree of denominator, as you can see, is less than degree of denominator. So first step is okay. After that, we need to factorize the denominator. So let's focus on factorizing the denominator. X square minus 9 in the denominator can be factorized as x plus 3, x minus 3. Okay. This is x square minus 3 square, right, which can be factorized as x plus 3, x minus 3, and this can further be broken down into two partial fractions, a upon x plus 3 plus b upon x minus 3. This is what you have. Is that okay? Yes, that's okay. What else? What will be the values of a and b from here? So a and b can be found with the help of comparison of numerators. 1 over here in the numerator is equal to a times x minus 3 plus b times x plus 3, as you can clearly observe, right? This is what you can observe. And now by simple comparing coefficient of x and and the constant term, coefficient of x, as you can see, is a plus b. On the left hand side it is 0, and here it is a plus b. Moreover, constant term 1 is equal to minus 3a plus 3b. Okay. So what do I observe? A plus b is equal to 0, and here I observe that a minus b is equal to minus 1 by 3, dividing by minus 3 throughout. So this becomes 1, this becomes minus 1, and this becomes minus 1 by 3. A minus b is known, a plus b is known, therefore a addition of these two will give me the value of 2a, which is minus 1 by 3, that becomes minus 1 by 6, and b over here becomes 1 by 6 with the help of this. Right, a and b have been found. Yes, a and b have been found. Okay, what else? Therefore, the integral will be equal to 1 upon x minus 3, x plus 3 dx. This becomes equal to integral of a upon x plus 3. A is minus 1 by 6. So, this becomes minus 1 by 6 upon x plus 3 plus 1 by 6 upon x minus 3 with respect to x. This is what we are looking to integrate. And this further becomes, okay, minus 1 by 6 will come out, integral of x plus 3 in the denominator plus 1 by 6 times integral of dx upon x minus 3. Now, this integral is not difficult, right? Minus 1 by 6 is okay. This becomes log modulus x plus 3 plus 1 by 6 log modulus x minus 3 is what I get, plus a constant term, right? And this is 1 by 6, this is 1 by 6. I can take 1 by 6 common. This is minus, this is plus. So, log of m minus log of n becomes log of m by n, which is equal to log modulus x minus 3 at the top and x plus 3. Because of this minus sign, using properties of log, this is what I get, plus constant term. That is my required answer for this. 1 by 6 log of modulus x minus 3 upon x plus 3 plus constant, and that's all. Yes, that is all that you have in this question, but one important thing, right? And what is that? I want to share one important thing with you, and that important thing relates to this, finding the values of a and b. How can we find the values of a and b easily? Is there some shortcut for doing that? Yes, there is a shortcut. So, let us look at that shortcut first. What do we have? We have 1 upon x plus 3 x minus 3 is equal to a upon x plus 3 plus b upon x minus 3. And let's suppose we want to find the value of a, just a. Okay, if you want to find the value of a, what I'll do is, I'll multiply with this x plus 3 throughout. So, x plus 3 will get cancelled from here, x plus 3 will get cancelled from here, and x plus 3 will come over here. First, this is what I'll do. I'll multiply with x plus 3 throughout. Okay. So, this becomes 1 upon x minus 3, this becomes a, this becomes b times x plus 3 upon x minus 3. And now, I'll put x plus 3 equals 0, which implies x equal to minus 3. Put x equal to minus 3 throughout. What does that give me? This becomes 1 upon, since this is true for all values of x, this is true for x equal to minus 3 as well, yes. So, this becomes 1 upon minus 3, which is minus 6, is equal to a plus this minus 3 plus 3 becomes 0, this overall becomes 0. And do you see that I directly get the value of a, which is minus 1 by 6? Yes? Oh, that was easy, yes. If you want to find the value of b, what will you do now? So, for finding the value of b, what I'll do is, I'll multiply throughout by this x minus 3, this x minus 3 will come over here, and this x minus 3 will get cancelled. Okay, this is not cancelled now, this exists and this does not exist. Okay, and now for finding the value of b, I'll put that x equal to 3. So, if x equal to 3, then what I get in the denominator, in the left hand side is 1 upon 3 plus 3, which is 1 upon 6, equal to a, the term with a becomes 0, and plus b, that gives me the value of b as 1 by 6. That looks pretty simple, yes. And is that some kind of a trick? We are following a proper method, just that we can skip a few steps and we can find the values of a and b easily using this idea. Now, how do we use this idea in general over here? So, finding the values of a, what you will do is, this x plus 3 equal to 0 happens at x equal to minus 3. So, you will forget this factor and you put x equal to minus 3 in the remaining expression on the left hand side, and what do you get? 1 upon minus 6, that gives you the value of a. Similarly, putting x equal to 3 here, after removing this will give you the value of b. So, imagine that x minus 3 has been multiplied, remove this x minus 3, therefore, do not worry about this, this will become 0 and you get the value of b as 1 upon 3 plus 3. That is the idea behind this, and this is how you can get the values of a and b in all such questions. Even in the previous question, when we go back to the previous question, I will show you how to get the value of a and b. Once again, let us see, with this question only, I will take you back to the previous question. So, here at this stage, what I will do is, if I want the value of a, I will multiply throughout with x plus 1. Okay. So, this becomes a 0 and after that I will put x equal to minus 1. So, this is removed, minus 1 upon 2 minus 1. What is that? Minus 1 upon 1. So the value of A should be minus 1. What about B? So we'll have to put x equal to minus 2 after multiplying with this. So minus 2 upon minus 2 plus 1. That is minus 2 upon minus 1, which is this 2. So that gives you the value of A and B. The idea we have discussed along with this question over here, and we have seen, okay, this exists. This is true for the previous question as well. You could see that. So finding values of A and B can be done using this approach as well, right? A pretty shortcut, you can say. Okay, but when you are solving for the board examinations, obviously will be you following this approach, not the shortcuts. You can check your calculations with the shortcuts, but yes, you'll have to solve with this approach only. And once you do that, yes, you get your correct answer. And that is all that you have in this particular question over here. The third question says integrate 3x minus 1 upon x minus 2 x minus 1 x minus 2 x minus 3. Now how do we integrate this particular expression? Once again, the first step, that first thing that you observe is whether the degree of the numerator is less than the degree of denominator. Yes. Whether the denominator has been factorized. Yes. Since first and second are okay, we directly want to convert into partial fractions and then we'll integrate. And in the previous question also we saw some shortcut to discuss the method of the shortcut of finding the values of A, B, and here you will also need C, right? So first let's write the expression in terms of partial fractions. 3x minus 1 upon x minus 1 is there, x minus 2 is there, then you have x minus 3 as well in the denominator. This is equal to what? This is equal to A upon x minus 1 plus B upon x minus 2 plus C upon x minus 3. This is what you have. A upon x minus 1 plus B upon x minus 2 plus C upon x minus 3. And for finding the values of A, B and C, we can use a shortcut. But before that, let's solve using the longer approach. Or do we solve with the shortcut first? Let's use the shortcut to get the values of A, B and C, and we'll verify as per the longer approach which is required for NCERT people, right? So let's use this small space. This space is required, yes. So finding the values of A, what do we do? Okay, we multiply by x minus 1 and we put x equal to 1. So these will become 0 and this will go, and A will be equal to, putting x equal to 1, this will be 3 minus 1 upon 1 minus 2 times 1 minus 3. What is that? This is 2 and this is minus 2. So that will become minus 1 upon minus 1. So the value of A is simply 1. B, for B, I'll go a bit faster. So we put x equal to 2, get rid of this. This is 3 times 2 is 6, minus 1 is 5 upon, this is 1 and this is minus 1. This is minus 1 over here. This tells me minus 5. Okay. Value of C will be putting x equal to 3 over here. This is 3 times 3 minus 1 is 8 upon 3 minus 1 is 2 and this is 1. So this becomes 4. So the values of A, B and C have been found. A equals to 1, B equal to minus 5 and C is equal to 4. But for the NCERT people, for the board people, if you want to solve, we'll have to use alternative approach to get the values of A, B and C. And what is that? So numerators have to be compared. Numerators 3x minus 1 will be equal to A times, oh, this numerator will be big, right? The LCM will be x minus 1, x minus 2, x minus 3. So will A, you will get x minus 2, x minus 3. Plus B times you will get x minus 1, x minus 3. Right or not? This and this. But C you will get x minus 1, x minus 2. And now do you see that the next step is to get the values of A, B and C by comparing the coefficients, or you can substitute some particular values of x, because this is always equal to this. This will be true for some particular values of x as well. Yes or no? Yes. So comparing the coefficients is one of the ideas. The second idea is put some particular values of x. Now putting some particular values of x, isn't that what we have done in the numerator? Yes, in this particular method. That's what we have done without actually using this system, right? So for example, if you wanted A, so what you will do is you will put the value of x as 1. This becomes 0, this becomes 0, this becomes minus 1, this becomes minus 2, which is overall 2. 2A is equal to 2. 3 minus 1 is 2, right? So 2A is equal to 2 implies A equal to 1. This is what you are getting, right? Exactly same thing will come over here. Similarly, value of B, value of C can be found by putting certain values of x. Otherwise, you can also compare coefficients. So compare. Compare tells me coefficient of x square on the right hand side and on the LHS. x square on the left hand side is 0, okay. So this is a times x square, b times x square, c times x square. That tells me, okay, a plus b plus c is 0. That's one thing. Coefficient of x is 3, which is equal to, this is minus 5x, this is minus 4x, this is minus 3x. So minus 5a, minus 4b, minus 3c is what I'll be getting. This is the next thing. And the last constant term is minus 1, which is equal to 6a, 3b, 2c. 6a, 3b, 2c. You see the level of calculations over there? We haven't yet obtained the values of a, b and c. We're just on the path of getting those values. And still we'll have to solve these 3 equations, 3 unknowns. Okay, that looks pretty difficult. Yes, it is not as such very difficult, because gradually once you start solving, you'll finally get the values of a, b and c. What you're supposed to do, you can eliminate c first of all, right? C is equal to minus a minus b, and this will convert to 3 equals minus a will become 3a and this will become 3b. So plus 3a, this is 8 minus 5a minus 2a, and plus 3b, this becomes minus b, right? This is what you get. And from here I'll get minus 1 is equal to 6a plus 3b minus 2a minus 2b. 6a minus 2a is 4a and 3b minus 2b is b. And adding these two will get, will eliminate b. 4a minus 2a will be 2a. 2a is equal to 2 will give me a equals 1, which will give me a equals 1. And that's one thing, a equals 1. Using this a equals 1 and any of these, you can get the value of b. Let's say b will be equal to minus 3 minus 2a. What is this? Minus 3 minus 2, which is minus 5. So a equals 1, b equals minus 5, and using these two you can get the value of c. So minus 5 plus 1 is minus 4, which will go over there and becomes 4. Therefore c is equal to 4. So have you found the values of a, b and c using this approach as well? Yes, the NCERT people love this approach. This is a equal to 1, b is equal to minus 5, c is equal to 4, which we found some time back as well, right? So we have verified these values. We are okay with this approach as well. But when we want to discuss the complete steps, we'll follow this approach, right? For the board people, right? Okay. For competitive exams, this is what you'll focus on, and this is how you'll get it done. So the expression has been simplified into partial fractions. Now is the time to integrate. So I, the integral, is equal to 3x minus 1 upon x minus 1, x minus 2, x minus 3 dx, and this converts to integral of a upon x minus 1. A is 1 upon x minus 1. B minus 5 upon x minus 2 plus c, which is 4 upon x minus 3 dx. And this integral can be separated out. This integral of this will be log of modulus x minus 1. Minus 5 goes away, 1 upon x minus 2. The integral will be log modulus x minus 2. 4 goes outside, integral of this will be log modulus x minus 3 plus constant of integration. And yes, that is the required answer for this particular question, as you can see over here. Mind you, the important thing, this method involves first finding partial fractions, and that is the calculation for that. Actually, this is the calculation for that. Right or not? Yes. And once you are experienced enough, you can directly move from this stage to this stage. Yes. You can find the values of a, b and c orally as well. Yes or no? Yes. So this is the third question for us, and that's a complete solution for this particular question. The fourth question says x upon x minus 1, x minus 2, x minus 3. And seeing this question, you would realize, okay, this looks pretty simple, sir. We can directly write the partial fractions using our idea. So I, which is equal to x upon x minus 1, x minus 2, x minus 3 dx will have to be written as sum of partial fractions. And what are those partial fractions which we want to look at? We want to look at, okay, x upon x minus 1, x minus 2, x minus 3 is equal to a upon x minus 1 plus b upon x minus 2 plus c upon x minus 3. Now for the board people, it is important how you represent your answer, what methods you apply. But for the competitive exam people, they're only interested in actually the solution, the final answer, right? So the final answer can be obtained easily. For this, the value of A, B and C can be obtained easily. For A will have to substitute x equal to 1 over here by removing this. So 1 upon minus 1 minus 2 is 1 upon 2. That's the value of A. B, the value is, we'll substitute x equal to 2 over here, 2 upon 1, 1 minus 1. This is 2 upon 1, 2 upon minus 1, which is minus 2. C, are we doing this orally? Yes, we are doing this orally, but I hope you get the idea. We've discussed this method in the previous 3 questions, right? So x equal to 3 will be substituted over here by removing this. This becomes 3 upon 2 into 1. 3 upon 2 is what I get. This is what I get, right? Okay, but this is a shortcut approach, sir. We'll have to write using a longer approach in the board examinations, and that longer approach looks like this. Please take a look at this. So we'll compare the numerators. X is the numerator, which is equal to this. Let's pack this in a box, and for the time being, let's forget about it. We never did this. So this numerator is equal to this on the right hand side, A times x minus 2, x minus 3 plus B times x minus 1, x minus 3 plus C times x minus 1, x minus 2 is what you get. Take a look at this carefully. This is the LCM, and after taking the LCM, only the numerators are compared over here. Okay, and once you see this approach, what are you going to do? In the next step, what you say is, okay, this is always equal to this, so why not substitute some particular values of x and get the values of a, b and c? You could do that. For example, if you substitute x equal to 1, this becomes 0, this equals 0. This is minus 1, this is minus 2. So this is 2a is equal to 1. So a becomes 1 by 2. Okay, that is what we have done in the numerator, but orally. Okay, but the NCERT people are lovely people, and they want you to solve using another approach for that matter. What's that other approach? By using comparison of coefficients. They say, okay, this is an identity, solve it like an identity. Don't use any shortcuts. So what we'll do is, we'll solve it using that idea by comparing. So comparing tells me that coefficient of x square on the left hand side is 0, and coefficient of x square is a x square, b x square, c x square. What do you have? 0 is equal to a plus b plus c. By comparing the coefficients of x square. By comparing the coefficient of x, that is 1 on the left hand side, what you get on the right hand side is minus 5a minus 4b minus 3c. Minus 5a minus 4b minus 3c. What next? The constant term on the left hand side is 0. The constant term on the right hand side is 6a, 3b, 2c. And once I reach this stage, what I'll do is simply solve the values of a, b and c from these 3 equations. Looks complicated, but it is not very complicated. We'll have to eliminate one of the variables using one equation. Let's use this equation. The value of c is minus a minus b. Let's substitute it over here. And this equation becomes what? 1 equals minus 5a minus 4b minus 3 times minus a minus b will be 3a plus 3b, right? So minus 5a plus 3a will be minus 2a, minus 4b plus 3b will be minus b. Oh, similar calculations were done in the previous question, right? Yes. Once again, this is minus 2a minus 2b because of this substitution. 6a minus 2a is 4a. 0 equals 4a, and 3b minus 2b is plus b. This is what you get. Adding these two, you get 2a equals 1, or a will be equal to 1 by 2. B is minus 4a, b is equal to minus 2. A plus b plus c is 0, so therefore c will be equal to 3 by 2. And this are the same. Yes, they were supposed to be same. They are exactly same. That's how you obtain the partial fractions, right? So this expression can be done as integral of a upon x minus 1, which is 1 by 2 over x minus 1. B over x minus 2, which is minus 2 over x minus 2, c over x minus 3, which is 3 by 2 over x minus 3 dx. Okay, and after reaching this stage, this is 1 by 2 is okay. So log modulus x minus 1, minus 2 is okay, this is log modulus x minus 2, plus 3 by 2 is okay, this is log modulus x minus 3, plus constant term, and that is my answer for this question. As you can see over here, this is the final answer for this particular question. Over here, 4th question. The fifth question says integrate 2x upon x square plus 3x plus 2. How do we integrate this? First thing to observe, whether the degree of numerator is less than degree of denominator, whether it is a proper rational function, the answer is yes. So there's no need of division. Next thing, whether the denominator has been written as a product of linear or quadratic factors. This is a quadratic factor, but can this be factorized further? The answer is yes, this can be factorized further, x square plus 3x plus 2. Yes, and what else? X square plus 3x plus 2 can be factorized further. Other than that, do we need anything else? No. Once we factorize, after that, we can convert it into partial fractions and then integrate. Okay. Now, some of you may disagree with this particular algorithm. When you see this kind of a question anywhere randomly, okay, this is present in the exercise of partial fractions, so we'll think partial fractions, sir. But in case we encounter this question randomly, is it necessary that we go with the method of partial fractions? The answer truly is no, it is not at all necessary that you solve this question using the idea of partial fractions. What you can do is you can also use idea of linear upon quadratic over here. In one of the previous exercises which we saw linear upon quadratic, and there we use the formula of 1 upon quadratic, right? So for converting this into perfect square, we'll have to write it as x plus 3 by 2 whole square 2 minus 9 by 4, which is minus 1 by 4. So this is x plus 3 by 2 whole square minus 1 by 2 square, right? This is what you'll get. In the denominator, you have the form 1 upon x square minus a square actually, right? Oh, but there is a linear in the numerator, so that numerator has to be written as a times derivative of denominator plus b first of all, right? There will be two terms, you can integrate those two terms separately, right? That's what you will do. But linear upon quadratic is an approach which you can obviously follow over here. Once again, coming back, this question will be still easier with the method of partial fractions once you have mastered that, right? So in case you encounter this question randomly also, you should be able to see that, okay, sir, this can be solved by linear upon quadratic, this can be solved by partial fractions. Which of the methods will be easier over here? So the easier method for solving this question will be partial fractions by the way in which I'll discuss, right? So we have x square plus 3x plus 2, and let's take a look at this particular solution from that perspective. So 2x upon x square plus 3x plus 2. This denominator, I'm not going into the details of factorization, but this denominator can be factorized easily by splitting the middle term. This is 2, so 2 into 1, this becomes 2x and plus x. So plus 2x plus x, that will give me one of the factors as x plus 2, the other factor is x plus 1. In the numerator, you have 2x, right? Now, once you have factorized, convert into partial fractions. So this becomes a upon x plus 2 plus b over x plus 1. Okay, what about the values of a and b? Oh, we need some shortcuts. We have some shortcuts for finding the values of a and b. So, our shortcut, let us find the values of a and b in this box over here using that idea. So, for a, you'll have to substitute x equal to minus 2 over here by removing this. Yes or no? Yes. So, x equal to minus 2, this becomes minus 4, and minus 2 plus 1, which is minus 1, that tells me a equals 4. What about the value of b? We'll put x equal to minus 1 over here by removing this. This is minus 2, this is 1. So, b equals minus 2 actually. Very interesting. Yes or no? Yes. So, a equals 4, b equals to minus 2 is what I get, and this is a shortcut approach, right? Once again, for the board people, they are once again very lovely people, and they want you to solve using another approach. So, let's see the comparison with numerators. Numerators, throughout 2x is equal to a times x plus 1 plus b times x plus 2 is what I have, okay. Comparison tells me that coefficient compare these two. So, in the right hand side, you have some term containing x and some constant term, right. So, term containing x, this coefficient of x will be 2, and on the right hand side it will be a plus b. On the left hand side, constant term is 0, on the right hand side, constant term is a plus 2b. Using these two, do you get the values of a and b? Yes. Subtracting will give me the value of b directly. B is equal to 0 minus 2, which is minus 2. And a, therefore, is equal to minus 2b, which is 4. A equals to 4, b is equal to minus 2. That's what we found, right? And that's the same thing. So, After this, yes, we have converted into partial fractions. Once we have converted into partial fractions, next we can talk about integration, which is 2x upon x square plus 3x plus 2 dx has been written as integral of a upon x plus 2, which is 4 upon x plus 2 minus 2 upon x plus 1 dx. This is what you get. Is that okay? Yes. So integration of this, okay, this is 4 times log modulus x plus 2 minus 2 times log modulus x plus 1 plus constant. That's my answer for this particular question. As you can see over here in this 5th question, that's a complete solution. First finding the partial fractions, obviously before that we have factorized, and then integration, right? That is all that you have in this question. The 6th question says we have 1 minus x square upon x times 1 minus 2x. And remember the steps for integration. Before integration, we need to check whether this is a proper rational function, that is, whether the degree of numerator is less than the degree of denominator. If not, you'll have to divide using long division first and then try to convert it into partial fractions after that. So, if I observe degree of denominator, that's x square, right? Degree is 2. Oh, here also we have an x square, so the degree of numerator is also 2. So we'll have to divide. Yes, we'll have to divide. So first step will be to divide. Okay, how do we do that? This is not a very complicated thing. As you can see over here, what you'll see is 1 minus x square upon, this is x minus 2x square. Okay, let's try to create this over here. Since we have to divide with this, let's try to bring some quotient, right? Let's try to write dividend as this. So if minus x square, if I want to write it as minus 2x square, I'll have to multiply it with 1 by 2. So this is 1 by 2, x minus 2x square is what I'll get. Since this is a pretty simple question, I'm solving it this approach, direct approach, right? So this is half times x minus 2x square, which is minus x square over here, which goes okay, plus x by 2 is extra, and we'll have to subtract that x by 2, right? So this is x by 2 is extra, so we'll have to subtract minus x by 2 over there. And what else? You have a plus 1 over here extra, right? And what do we have in the denominator is x minus 2x square. This is what you have. Is that okay? Yes. Now dividing this becomes 1 by 2 separate. And let's take a minus common over here. Minus 1 by 2 also common over here. Okay, so minus 1 by 2 will make it x minus 2 in the numerator over here. So this becomes x minus 2 in the numerator. In the denominator, you have x minus 2x square, which can be done as x times 1 minus 2x again. Okay, so this is one term. The integral of half is pretty simple. The integral of this expression has to be found. For finding the integral of this, we'll have to write this as sum of partial fractions, right or not? Yes. Let's try to do that. Oh, we could have used linear upon quadratic as well. Yes, that is something which we discussed in the previous question, that this type of question could be solved using linear upon quadratic ideas by converting denominator into a perfect square. But before that, writing the numerator as a times differential coefficient of denominator plus b. But that approach as compared to partial fractions will be slightly longer. So we'll prefer, in general also, if we get this kind of question, we'll prefer this approach which I am discussing now. That is the approach of partial fractions. Okay, so this particular expression now, and we want to focus on this expression. This becomes x minus 2 over x times 1 minus 2x. This has to be written as, this is a linear term, a upon x plus b upon 1 minus 2x. Okay, and finding the values of a and b is important now. So the next thing is to find the values of a and b, and we know some approaches to find the values of a and b, some shortcut approach, some long approach. So which of these approaches do you think will we follow? So we can follow any of these. The NCERT people love the longer approach, but we have the shortcut approach as well. Let me give you this particular solution with shortcut approach first. So for finding the values of a, we'll multiply with x, and this becomes, this x goes away, we'll substitute x equal to 0, right? This denominator becomes 0 at x equal to 0. So this is minus 2 upon 1. So a is equal to minus 2 using shorter approach, and b is equal to what? For b, this 1 minus 2x becomes 0 at x equal to 1 by 2, right? So this will go over there, remove this, put x equal to 1 by 2. So this is 1 by 2 minus 2, which is minus 3 by 2 upon 1 by 2, which is minus 3. This tells me b is equal to minus 3, right? And what about the longer approach? Using the longer approach says numerators have to be compared. That implies x minus 2 is equal to a 1 minus 2x plus bx. Okay, and now compare the coefficients of x and constant term. Compare. Coefficient of x is 1, which is equal to minus 2a plus b. Constant term is minus 2, which is equal to a. So a is directly obtained as minus 2. We substitute a as minus 2. This becomes 4, which goes over there. B will be minus 3. Oh, this is also simple. Yes, in this question, this and this both are simple because there are only two terms, right? Therefore, we have written this complete expression as sum of two partial fractions, and now I can integrate this. Therefore, I, which was actually equal to this 1 minus x square over x times 1 minus 2x dx has been simplified as 1 by 2 separate minus 1 by 2 times this expression has been simplified as a upon x. A is minus 2 upon x plus b, which is minus 3 upon 1 minus 2x, and integral of this whole expression with respect to x is what we are looking forward to. How do we integrate this? Let's simplify this a bit further. This is 1 by 2 minus 1 by 2 into minus 2 is plus 1 by x, and minus 1 by 2 minus 3 is plus 3 by 2, 1 upon 1 minus 2x over here. This is what you have, dx, right? So this integral is simple, this integral is simple. What about this one? This is a linear expression of x, right? The coefficient of x is minus 2. We'll have to divide with that minus 2 at the end. That's something you shall be doing, right? So integral of 1 by 2 becomes x by 2. 1 by x becomes log modulus of x plus 3 by 2 log modulus 1 minus 2x, and divide with the minus 2. This particular term has to be divided. So dividing with minus 2 is important, plus constant term. Or this can further be simplified as x plus 2, x by 2 plus log mod x minus 3 by 4 log modulus 1 minus 2x plus constant. That is the required answer for this particular question over here. And that is how you solve. The process is important. You see, integration only occurs over here. Once that function has been converted into an integrable form, therefore, then comes the condition, then comes integration. Actually, integration in itself is not difficult. The difficult thing is here only, that is conversion. First of all, identifying that this can be converted into partial fractions, and then conversion into actual partial fractions is what you are looking forward to. After that, integration becomes very easy, right? That's all that you have in this particular question, as you can see. Question number 7 says, integrate x upon x square plus 1 into x minus 1. Okay, so you have a quadratic factor in the denominator. You also have a linear factor in the denominator. The first and foremost important thing that we were supposed to note is whether it is a proper rational function, whether the degree of numerator is less than the degree of denominator. It says yes, the degree of numerator is less than the degree of denominator. Next thing, so we'll have to factorize the denominator, which is already factorized. Oh, this is a quadratic factor, but mind you, this cannot be factorized further. Yes, the partial fractions of this particular will be written in a particular way. Let's see what that particular way is, because that's the next step, right? Converting into partial fractions, and then we'll go for integration, right? So what do we have? We have x over x square plus 1 times x minus 1. Okay, this will be converted to, one of the factors will be this x minus 1. So a over x minus 1, and plus, since this is not factorized further, you'll have x square plus 1 in the denominator over here. And in the numerator, you have a linear expression, mind you, bx plus c. Okay, don't make a mistake over there. Okay, and in the previous questions, we used some shortcuts, right? So here, you can use that shortcut for finding the value of a, that is, multiply throughout by x minus 1 and put x equal to 1. 1 upon 2 is what you'll get, that will be the value of a. But for values of b and c, yes, you will have to worry a bit. So for that, the original method, come back to that and see where does the take us. So this tells me that x, the numerator will be equal to a times x square plus 1 plus bx plus c times x minus 1. This is on comparison of the numerators. After taking LCM over here, the denominators get cancelled and you get a times x square plus 1, x minus 1 times bx plus c in the numerator, right? And now I can compare, since this is always equal to, this LHS is always equal to that RHS, I can compare these two and see where does that take me. So I have a, b, c as two unknowns, so I need three conditions. The three conditions would be coefficient of x square compared on the both sides, coefficient of x, coefficient of, constant term, right? So coefficient of x square over here is 0, which is equal to ax square and bx square. This is a plus b. 0 is equal to a plus b. Coefficient of x is 1, which is equal to, over here, there is no x over here, there is minus bx plus cx. So this is c minus b over here, right? And the constant term, as you can see, is 0 on the left hand side. Constant term here will be a minus c. Okay, this is what I am getting, a minus c. Is that okay? Yes. So we can eliminate any two things for that matter. Let's say you can use these two equations to eliminate c and get equation in terms of a and b. This is another equation in terms of a and b. Using those two, we'll get the value of a and b. So adding these two, what do I get? Minus c plus c will get cancelled. A minus b is equal to 1. This is what I get. Okay, and a plus b is equal to 0. This tells me, okay, a plus b is equal to 0. Using these two, I can add them and get the value of a as 1 by 2. Oh, but this is what we started with, right? Yes, yes, yes. So a is 1 by 2, that's clear. What is b? B, as you can see, will be minus a, which is minus 1 by 2 using this. What will be the value of c? C is equal to a, therefore c will be equal to 1 by 2. Those are the three values that you need, right? That's the first thing. So you have converted the complete expression into partial fractions. And this linear is very easy to integrate. This linear upon quadratic, we know how to integrate this one. Yes, linear upon quadratic can be integrated with the help of ideas which we have discussed in the previous exercise. That is, the linear, this numerator can be written as something times derivative of this denominator plus some constant, right? We generally use a and b over there. So this can be done. A and b, since they have already been used over here, we'll use p and q. Let's say, so numerator equals p times derivative of denominator plus q is what you'll use over here, right? So that's the next step. Let's write the integral I, which is equal to this, or that becomes equal to what? That becomes equal to a upon x minus 1, integral of a, which is 1 by 2 over x minus 1 plus bx plus c, which is minus half x plus c, which is half upon x square plus 1 dx. This is what you have, right? This is what you have over here. Okay, what else? So this can be integrated easily. Half times this becomes log modulus x minus 1. This integral is pretty simple. And you can take out a half common from here. Exactly, you can take out a minus half common from here. So it becomes minus half integral of what remains is x minus 1 upon x square plus 1 dx. Okay. Now this x minus 1 has to be written as p times, or what we used over there was a times derivative of this denominator plus some b, right? So let me rewrite that x minus 1 as a times derivative of this, which is 2x plus b. And once again comparing tells me that, comparing both the sides tells me that 2a will be equal to 1, a will be equal to 1 by 2 over here also. Okay, but we have used a, b and c over here, so why are you using a, b, c over there also? So this particular calculation can be done in the rough as well. Okay, that's one of the ways, or you can use different variables. In the past we have used a and b, but here what you can do is you can use p and q as well. Doesn't make a difference. We are supposed to find the values of p and q, and let's do it. So 2p is equal to 1, which implies p is equal to 1 by 2, and q is equal to minus 1. That's what you can observe. Q is equal to minus 1. So using these values, I can write that second integral in terms of these two values. So therefore I, which is equal to half times log modulus x minus 1 minus 1 by 2 is okay, and this integral will be separated as half times 2x, okay, half times 2x, and you have minus 1 which is extra. So minus 1 upon this, upon x square plus 1, that's one term, and you have minus 1 upon x square plus 1 times dx. This is what you get, right? That's the complete integral. So this x square plus 1, if it is substituted as t, this 2x dx will become dt. So this is dt upon t. Integral is pretty simple. Yes, half is okay, log modulus x minus 1 is okay, minus 1 by 2 is okay. In the bracket, what will we have? This is half, okay, and this becomes dt upon t, which is log of mod t, or log of mod x square plus 1. This. This minus half remains as it is, and you have this particular term. Integral of this is nothing but tan inverse x plus a constant term, and yes, that is my final answer. Or you can just multiply this half inside and see this is half log of modulus x minus 1 minus 1 by 4 log modulus x square plus 1 minus of half into minus 1 is plus 1 by 2 tan inverse x plus constant. That is my required answer for this particular question, 7th. As you can see, the complete solution over here. Question 8 says integrate x upon x minus 1 square into x plus 2 in the denominator. Okay, so in the denominator you have linear factors, the degree of numerator is less than degree of denominator, therefore it is a proper rational function. First thing, okay. Second thing, denominator has been factorized, that's also okay. So now we'll convert it into partial fractions and then we'll integrate, yes. So let's try to write this expression x upon x minus 1 square x plus 2 as partial fractions. And how do you divide this into partial fractions? Okay, this x plus 2 is single, so it will not be a worry. This x minus 1 is a square, so we'll have to write a upon x minus 1 plus b over x minus 1 square. Okay, this is what we'll write it as. There's no need of bx plus c over here. What else? Plus c upon x plus 2. That's the form in which this will convert. Right, that's the form. This is something which you should remember first, that if you have a linear factor and it's a square, you write a upon x minus 1, b upon that linear factor squared, right? That's what you do. And after this, finding values of c will not be difficult. Finding value of b will also not be difficult. What you can do is you can simply multiply with x minus 1 square. What are we doing? We are multiplying with x minus 1 square, right? This will have x minus 1 remaining, this will have x minus 1 square, and x minus 1 square goes from here, and we'll put x equal to 1 to get the values of b, which is 1 upon 3. So b, using our shortcut ideas which you have discussed before, b will be 1 by 3. C can be substituted by multiplying with x plus 2 throughout, and multiplying by x plus 2, then substituting x equal to minus 2, we will get minus 2 over, this is minus 2 minus 1, which is minus 3 square is 9. So c will be equal to minus 2 upon 9. Something which you can do directly, right, by using the shortcut ideas which you have discussed in the previous questions. But here, the other important thing which remains is a. So can you find a in using that approach? No, the answer lies in, okay, we can multiply with x minus 1, but there will be x minus 1 remaining over here, there will be another x minus 1 remaining over here. So will we be able to substitute x equal to 1 over there? No, you will have zeros in the denominator, which is not okay. Therefore, we could find b but not a, yes. So once again, the NCERT people love the longer approach, and we can follow that longer approach whenever we want. But here, another shorter approach for finding the value of a, what you could have done is simply maybe substitute the value of x as 0, yes. Since you already have b and c, you can get the value of a easily. This LHS will become 0. Oh, this is an identity in terms of x, so this is true for all values of x, so I can substitute anything. Therefore, I can substitute 0 as well, yes. That is another idea to get the value of a. Right. But the longer approach which says, okay, that numerator x will be equal to what? Here, you'll have to take the LCM of x minus 1 square, x plus 2. So a will have x minus 1 times x plus 2 over here, plus b will have x plus 2 only, plus c will have x minus 1 square. Please note this, yes, this is what it will have. So there's x minus 1 missing over here, x plus 2 missing over here, that comes over here, there's x plus 2 missing, that comes over here, x minus 1 square comes over here. Right, that's the LCM. Now we can compare. Now what does comparison tell me? Comparison tells me, okay, compare the coefficients of x square, coefficient of x, and the constant term. So coefficient of x square is 0 on the left hand side, as you can see. Okay, there's no term of x square on the left hand side. What about the right hand side? There's x square over here, there's no x square over here, there's x square over here. So a x square plus c x square is what I have, right? Coefficient of x is 1 on the left hand side. What is the coefficient of x on the right hand side? This is 2x minus x. This is 1x into a. This is ax plus bx, and what do we have? Minus 2x, so minus 2cx. This is what you have, right? What about the constant term? The constant term is 0 over here. The constant term is minus 2a over here. The constant term is plus 2b over here, and the constant term is plus c over there, right? So you have 3 equations and 3 unknowns, and this particular equation only has a and c, right? So one of the things is we can substitute c in terms of a, and then maybe we can eliminate B as well, right? First we can eliminate C, then we can eliminate A. Or since this is already eliminated B, so we can eliminate B from these two, right? Which of these will be easy? Anyone for that matter, right? So what I'll do is I'll eliminate C from these two equations. These tell me, okay, C is minus A, so this becomes 2A plus A is 3A plus B, which is equal to 1. What else? Here I'll have minus A, so this becomes minus 3A plus 2B, which is equal to 0. Adding these two will give me 3B equal to 1, or B will be equal to 1 by 3. And A can also be found from here. What I'll get is 1 minus 1 by 3 is 2 by 3, and by 3 A will be equal to 2 by 9. And then using this, C will be equal to minus A, that is C is equal to minus 2 by 9. This is what you get. Oh, C is equal to minus 2 by 9, we found that. B is equal to 1 by 3, we already found that using a shortcut approach. Yes, yes, right. So this is the complete partial fractions. Okay, this is the step of partial fractions. Integral I, which was x upon x minus 1 square x plus 2 dx will become equal to integral of, this is A upon x minus 1, A is 2 by 9 upon x minus 1, B which is 1 by 3 upon x minus 1 square, and C which is minus 2 by 9 upon x plus 2 dx. This is what we have. Is that okay? Yes. So this is 2 by 9 log modulus x minus 1 plus 1 by 3. Okay, this is dx. Okay, we have to divide with the coefficient of x. The coefficient of x is 1, that's not an issue. Here you have 1 upon x square kind of thing, right? So the integral will be equal to x power minus 1 upon minus 1, which is 1 upon x with a minus. This is minus 1 upon x, right? So what you'll get is minus 1 upon x minus 1 as the integral of this. This is minus 2 by 9. Integral of this will be log of modulus x plus 2 plus a constant term. That's my final answer. Okay, this can be written as minus 1 by 3 x minus 1, and let me write that step as well. This is 2 by 9 log modulus x minus 1 minus 1 by 3 times x minus 1 in the denominator, right? And minus 2 by 9 log modulus x plus 2 plus constant term. That's the required answer for this particular question, as you can see over here. The ninth question says integrate 3x plus 5 upon x cube minus x square minus x plus 1. How do we do that? Okay, the degree of the numerator, as you can see, is less than the degree of denominator, therefore it is a proper rational function. First thing done. Okay, the next point says that factorize the denominator. Can we factorize the denominator? Yes, the denominator has not been given factorized, right? So we'll have to factorize that. And if you observe, you take a minus common from here, this is x minus 1, you take x square common here, this is x minus 1. So you'll get x minus 1 times x square minus 1, right? Okay, so let's begin with this. 3x plus 5 over x cube minus x square minus x plus 1, and that is further equal to what? This is further equal to 3x plus 5 upon, you can take out x square common from here, x minus 1 therefore will come out common, and what will remain is x square minus 1, right? But is that it? No. This can further be factorized. Yes, this can further be factorized. But let's check this. This is x cube minus x square plus 1. Yeah, right. So I can factorize this further. This becomes 3x plus 5, which is okay. In the denominator, this will be converted to x plus 1 times x minus 1. X minus 1 will be x minus 1 squared, right? So you have converted into, let us say, converted the denominator as linear factors. That's it, right? There are no quadratic factors or linear factors. Next step is to write them as partial fractions. Let's do it. Let's do it. This is further equal to what? This is further equal to, okay, therefore 3x plus 5 over x plus 1 times x minus 1 squared can be written as what? This can be written as, please observe, a over x plus 1 plus b over x minus 1 plus c over x minus 1 squared. This is a linear factor, but it is squared, this there. So we'll add terms of x plus 1, x minus 1 and x minus 1 square in the denominator. Numerators will be constants only, a, b and c. And this is always equal to this. This is always equal to this. Therefore, what will we do? We'll try to find the values of a, b and c by, one of the ideas is simple common sense. Yes, That is the shortcut that we can have, or we can use the method of finding this by comparing coefficients in the numerator, right? So numerators in the left hand side is 3x plus 5. In the right hand side you have a times x minus 1 squared plus b times you have x plus 1, x minus 1 plus c times you have x plus 1. And now you can compare. So comparing involves what? Comparing involves this, that coefficient of x square is a, coefficient of x square is b, coefficient of x square is not there, right? There is no coefficient of x square on the left hand side, therefore 0 is equal to a plus b over here, right? That's first thing that I observe. The next thing is coefficient of x, which is 3, will be equal to minus 2ax, okay, and there is no x term from here, there is a term x from the c, right? Constant term is 5, which is equal to, okay, there is x square, so 1, that is 1a, this is minus b and plus c, that's what we have, right? Is that okay? Yes. So we can eliminate certain things, and can we eliminate c from here easily? Yes, that's something which can be done. Or we can eliminate b from these two, that's also possible, right? Whichever way you want to go. So let's eliminate c from here. By subtracting this from this becomes 2 is equal to a plus 2a, which is 3a minus b. And we have 0 is equal to a plus b over here. So adding these two gives me 4a equal to 2, a will be equal to 1 by 2. Okay, b will be equal to, as you can see from here, will be minus 1 by 2. And c can be obtained with the help of this. C is 3 plus 2a, 3 plus 1, 4. C will be 4. Is that okay? Yes, please note this carefully. 3 plus 1, 4 is what I get. Yes, yes. So we have factorized the denominator, we have converted them into partial fractions with the help of this step, and therefore finding the values of a, b and c. Now is the turn of integration. Yes. So let's integrate. I is equal to integral of that whole expression 3x plus 5 over x cube minus x square minus x plus 1 dx, and that expression has been further converted into this, which is a 1 by 2 times okay x plus 1 integral of 1 dx upon x plus 1 is what I have. Okay, then you have b, which is minus 1 by 2, so that becomes minus 1 by 2 integral of dx upon x minus 1. I am writing them as separate integrals. Then you have plus c integral dx upon x minus 1 square. And now we can see the separate integrals easily, right? So this becomes half log modulus x plus 1 minus half log modulus x minus 1, and you have this becomes minus 1 upon x minus 1. So minus 4 upon x minus 1 plus constant, and that is the required answer for this particular question over here. This is a 9th question for us, and that's a complete solution for this question. The 10th question says integrate 2x minus 3 upon x square minus 1 times 2x plus 3. Now how do we do that? Once again, whether the degree of numerator is less than the degree of denominator. Yes, so this is a proper rational function. Whether the denominator has been factorized. Oh, there's x square minus 1 which can be factorized further. So let's do it. And after that factorization will convert into partial fractions, right? So 2x minus 3 upon, this can be done as x plus 1, x minus 1, 2x plus 3. Is that okay? Yes, that looks okay, right? What else? So this is equal to a upon x plus 1 plus b upon x minus 1 plus c upon 2x plus 3. Those are the partial fractions, and next target is to find the values of a, b and c. So a, b and c can be found by a simple idea that we have discussed in the previous questions. That is, I'll explain that once again. What do we have? So for finding the value of a, what we do is we divide with this x plus 1 throughout. So this goes away, yes. There is x plus 1 over here, this is x plus 1 over here. So we put x plus 1 equal to 0, that is x equal to minus 1 throughout. This becomes a 0, this becomes a 0, this is a equals, this goes away, you get minus 2 minus 3 minus 2 minus 1, this is minus 5 upon minus 2, which is 5 upon 2, and what do you get? This is 1, right? So then you get a 5 by 2, which is the value of a. And similarly, you can find the values of b and c using that shortcut approach. But then, the lovely people, NCERT people and the CBSE board people, they wanted to solve using some other idea. In the competitive exams, you can obviously use this approach, but for the NCERT people, what we'll do is we'll compare the numerators. So in the numerator, we have 2x minus 3 over here, yes, and in the numerators over here, what we'll have a times x minus 1 times 2x plus 3 plus b times x plus 1 and 2x plus 3 plus c times what do we have, x plus 1 x minus 1, which is actually x square minus 1. This is what you have. Is that okay? Yes. Now we can compare the coefficient of x square, the coefficient of x and the constant term. Yes. So compare. Coefficient of x square is 0 on the left hand side. Yes. What about right hand side? Right hand side we have ax 2x, which is 2a x square. This is 2b x square. This is c x square. So 2a plus 2b plus c is what I get. Okay. The coefficient of x is 2 over there, which is equal to, okay, you have 3x minus 2x, which is x into ax. You have 5x over here, 5bx, and there's no x. So there's a plus 5b. The constant term, which is minus 3 over there, is equal to minus 3a plus 3b minus c. Minus c. Is that what you get? Yes, that's what you get. Now, let's find the values of a, b and c by solving these equations. So this is ab, this is ab, this is ab, this is c as well. So we can eliminate c from these two. Yes. Adding these two, what do you get? Minus 3 is equal to minus a plus 5b. Okay. And using this with this, add them together, minus a and a gets cancelled. 10b is equal to minus 1. So you get the value of b as minus 1 by 10. Using this b, I can get the value of a from here. A will be 3 plus 5b, right? 3 minus 5 by 10, 3 minus 1 by 2, which is 5 by 2. A will be equal to 5 by 2. And using these two values, I can get the value of c as 2a plus 2b with a minus. So 2a is 5, 2b is minus 1 by 5. So 5 minus 1 by 5, what will that be? 24 by 5. And with a minus, c will be minus 24 by 5. Let's check this value of c again. 2a is 5, 2b is minus 1 by 5, and 5 minus 1 by 5 will be 24 by 5. You could take that on the left hand side and you get minus 24 by 5. This is the value of c. Yes. Okay. This is comparison. This is a 10th question for us. Is that okay? Yes. What else? So next thing that we need is the integral. I is equal to integral of that whole expression, which is 2x minus 3 over x square minus 1 times 2x plus 3 dx, and this converts to this, which converts to this, where a, b, c are as shown. So this integral will be equal to a upon x plus 1, which is 5 by 2 upon x plus 1. Then you have b upon x minus 1, which is minus 1 by 10 upon x minus 1. And you have c, which is minus 24 by 5 upon 2x plus 3 times dx. This is what you have. And where does that take us? So this is 5 by 2 log modulus x plus 1 minus 1 by 10 log modulus x minus 1, and minus 24 by 5 is okay. Log modulus 2x plus 3 is also okay, but this 2x plus 3 will leave a 2 in the denominator over here plus constant term. So this converts to 5 by 2 log modulus x plus 1 minus 1 by 10 log modulus x minus 1 and minus 12 by 5 log modulus 2x plus 3 plus constant. That is my required solution. That's the final answer for this particular question, as you can see over here. In the 11th question, we have 5x upon x plus 1 times x square minus 4. Now once again, this x square minus 4, yes, that can be factorized further. Let's do it. So 5x upon x plus 1 is okay, and this is x plus 2 times x minus 2. That's the factorization of x square minus 4, which is equal to, in terms of partial fractions, will be equal to a upon x plus 1 plus b over x plus 2 plus c over x minus 2. And using the concepts of comparison of numerators and denominators, so what you can do is numerator. By the way, yes, we could have used the shortcut. Yes, what is that? So we'll get rid of this x plus 1, put x equal to minus 1 to get a. So that is minus 5 upon minus 3 and minus 3, and this is 2 minus 1, which is 1. So minus 5 upon minus 3, which is 5 upon 3. So a will be 5 by 3. Similarly, b A will be 5 by 3, B will be, you can observe x plus 2, so that goes away, minus 2 is minus 4, and minus 2 plus 1 is minus 1, so minus 1 minus 4 will be 4, and this becomes minus 10. So minus 10 by 4 will be minus 5 by 2. And C will be 2, this goes away, this is 4, 5, 6, sorry, this is 2. So 4 times 2 is 8, and 5 times 2 is 10. 10 upon 8 is 5 by 4. So C should be equal to 5 by 4. That is what we seem to be getting here, right? This is what we seem to be getting here. Let's see. By comparison of numerators. Numerators, we have 5x, which is equal to a times this minus this into this, which is a times x square minus 4. Plus b times, we have x plus 1 times x minus 2. Plus c times, what do we have? X plus 1 times x plus 2. Yes. Now let's compare the left hand side and the right hand side. Coefficient of x square, coefficient of x, and constant term. So compare coefficient of x square is 0, which is equal to ax square, bx square, cx square, which is a plus b plus c over here. Coefficient of x, which is 5, is equal to, there is no x over here, there is minus x over here, minus bx, and there is 3x. So minus b plus 3c is what you get. Constant term, that is 0 on the left hand side, which is equal to minus 4a, and you get minus 2b plus 2c. This is what you get. Is that okay? Yes. What else? So this equation has ABC, this equation has B, AB is C, and this equation has B and C only. So we'll have to eliminate anyone. Let's say, can we eliminate B from here? Yes, that can be done, or we can eliminate A from these two equation by multiplying this with 4 and adding, right? So multiply this with 4. What does that give me? 4a plus 4b plus 4c equals 0. And from this and this, what does that give me? 4a minus 4a gets cancelled. Okay, that goes 4b minus 2b is 2b plus 6c is equal to 0. Right? That's what you get. Or you can say b plus 3c is equal to 0. There's another thing which says minus b plus 3c equal to 5. So minus b plus 3c equals 5. These two tell me that 6c will be equal to 5, or c will be equal to 6c. C will be equal to 5 by 6. That's what you'll be getting. 5 by 6. Is that okay? Let's check that value. C will be equal to 5 by 6. Oh, C is 5. No. Let's check that value. C is equal to 5 by 4. So here what we did was we substitute x equal to 2 over there. This is 2 into 2, 4. This is 2 plus 1, 3. Okay, 2 into 3 is 12, not 8. Sorry, 4 into 3 is 12, not 8. In the previous thing, what is it? This was taken as 2, right? So there's no 8 in the denominator, there's a 12 in the denominator. 10 will get cancelled and this becomes a 6, right? So there was a mistake over there. This is okay. This is 5 by 6. What about the value of B? B is minus 3c. Okay, so B is minus 3 times this. So minus 5 by 2 is what I get. And that looks okay. Yes. What about the value of A? A plus B plus C is 0. So this plus this is what I am interested in. Yes. And what do we get? So 5 by 6 minus 15 by 6. This is 5 by 6 minus 15 by 6, which is minus 10 by 6. Minus 10 by 6, and you multiply with the minus, that becomes 10 by 6, which is 5 by 3. So A is 5 by 3. Yes. That looks okay. These are the values of A, B and C, right? Let's keep them over here. And now we look at integration. Therefore, I is equal to integral of that expression, or that becomes this becomes this, and that can be written as A upon x plus 1, which is 5 by 3 upon x plus 1. B upon x plus 2, which is minus 5 by 2 upon x plus 2, plus C, which is 5 by 6 over x minus 2 times dx. This is the integral. That becomes 5 by 3, which is okay. 1 upon x minus 1, the x plus 1, the integral is log modulus x plus 1 minus 5 by 2 log modulus x plus 2 and plus 5 by 6 log modulus x minus 2 plus constant term is what I get as the final answer for this particular question. You can see the integration step is not at all difficult. The important thing is that you identify this as a question based on partial fractions first. identify. Here we are solving the exercise based on partial fractions, so it's not difficult, but in general such rational integrals can be easily handled with partial fractions. Finding the values of a, b and c, and the integration part is pretty simple, as you can observe over here using this question. In the 12th question, what do we have? X cube plus x plus 1 upon x square minus 1. And yes, there comes the interesting thing. What is that? So the first thing which we wanted to check was whether the degree of numerator is less than the degree of denominator. It's not so. So we'll have to divide the numerator with the denominator using log and division. Yes, that's the approach that you can follow. So we have x cube plus x plus 1 upon x square minus 1. This x cube plus x plus 1 can be written as a factor of x square minus 1. X times x square minus 1. Let's take care of this x cube first. What do you have? Is x cube on the left hand side. You get an extra minus x on the right hand side, right? So you get extra minus x. You need a plus x. So what you do is plus 2x. And there was a plus 1 as well, right? So that's what you get, right? This is a quotient. This is a remainder when you divide with x square minus 1. Yes. So this is x square plus 1 over here. And this is x square plus, sorry, minus 1, not plus 1. X square minus 1 is over here. Yes and yes. And this further simplifies to, on dividing this by this, you get x. On dividing this, remaining thing, this is 2x plus 1 upon x square minus 1. Okay. And what next? So this integral is pretty simple. Yes, this is integrable. What about this remaining one? This can be handled using two approaches. One of the approaches says that you can factorize the denominator and use the concept of partial fractions. The other approach says, why worry about that? What you can do is, this is linear upon quadratic, right? And you can use idea of linear upon quadratic. Since x square minus 1, the derivative is 2x. Yes, this is already written in that particular form. So 2x can be handled separately. 2x upon x square minus 1. This is derivative upon this. It becomes dt upon t, which is log mod t. Simple. 1 upon x square minus 1 is similar to 1 upon x square minus a square. Yes, and you know the formula for that. But do you also know, do you also see that that formula is derived by using no other concept than partial fractions, right? No other concept than partial fractions. So yes, at the end of the day, we'll be using partial fractions one way or the other. In the formula, it is already embedded, so that's also okay. What do we want to do over here? What we can do is, let's solve it using the easier approach. Why not? So I will be equal to integral of x plus 2x upon x square minus 1. This is the derivative of this, plus 1 upon x square minus 1 dx. Right? This is what I'll get. And this is equal to x, the integral is x square by 2, plus this becomes 2x dx, which is derivative of nothing but x square minus 1. So this is dt by d, which becomes log of modulus x square minus 1. And what does this become? Plus 1 upon x square minus a square. The integral was 1 upon 2a log of modulus x minus a upon x plus a. That's what you'll use over here. The identity that I'm talking about is this. 1 upon 2a log modulus x minus a upon x plus a plus constant. This is what you have. So a, instead of a, you have a 1 over here. So 1 upon 2a is 1 upon 2 into 1, which is this, log of modulus, what you have is x minus a, which is x minus 1 upon x plus 1 plus constant term. That's my required answer using this direct approach. This is using this direct approach, mind you, and that's the complete solution of this question. But what about partial fractions, sir? Could we have solved using this, this question using partial fractions as well? Yes, this question could have been solved using partial fractions as well. Let me get rid of this whole thing, this formula, and then using this remaining space, I'll show you the solution using the idea of partial fractions as well. So after this stage over here, once you divide this, I'll convert this into partial fractions. So 2x plus 1 upon x square minus 1, which can be written as 2x plus 1 upon x plus 1 x minus 1. This can further be factorized into, further written as fractions a upon x plus 1 plus b upon x minus 1. And the values of a and b are important. That is something which you can find directly or indirectly, as we know. So b will be equal to, remove this, 3 upon 2 by substituting x equal to 1. And a will be equal to minus 1 upon minus 2, which is 1 upon 2, right? So you can use those ideas, or you can compare the numerators. 2x plus 1 is equal to a times x minus 1 plus b times x plus 1. And using coefficient of x 2, which is a plus b, coefficient constant term 1, which is equal to minus a plus b, what do we get? B is 3 by 2, as we said initially. A is, you can see this is 1 by 2, right? So a and b have been found, yes, and we have written the complete integral as sum of partial fractions, right? So therefore I, using this alternative approach, the yellow one, what do we get? I, which is that integral, becomes equal to this, x plus this expression, which is equal to a upon x plus 1, which is 1 by 2 upon x plus 1 plus 3 by 2 upon x minus 1 dx. This is what you get, right? And the integral of x is x square by 2 plus half, this is log modulus x plus 1 plus 3 by 2 log modulus x minus 1 plus constant, and that is the required answer. Oh, you would say, so this answer looks pretty different, is it? Yes, they look different, but they are exactly same. How do we observe that? This is x square minus 1, right? So this can be done as x plus 1, x minus 1. So what I'll get is log of x plus 1 times log of x plus 1 plus log of x minus 1 is what I'll get from here. And with this, combining with this is half of log x minus 1 minus half log x plus 1. So 1 minus 1 by 2 will be 1 by 2 log x plus 1, and 1 plus 1 by 2 log of, this is 3 by 2 log of modulus x minus 1. They're exactly same, looking different, but they're exactly same. So both of these approaches are correct, and you can solve the question using any of these. That's okay, right? That's a complete solution. That's a complete solution using first method and the second method for this particular question. Let's continue with the next question of this exercise 7.5 from the chapter integrals for you. Question number 13 says 2 upon 1 minus x, 1 plus x square has to be integrated, okay? And in the previous questions that we have discussed, we have seen the steps related to solving integrals of rational functions. Rational functions which are polynomial upon polynomials. If the degree of numerator is less than the degree of denominator, it is called a proper rational function. Yes, this is a proper rational function. The next thing is, this denominator has to be factorized into linear and quadratic factors. Yes, it has been already factorized into linear and quadratic factors. This cannot be factorized further. 1 plus x square is the maximum limit at which, right? And after that, obviously, we'll have to convert these into partial fractions. And once we convert them into partial fractions, then we can integrate, right? So those are the steps that will follow. 2 over 1 minus x times 1 plus x square. I begin with this, which is equal to what? This will be equal to a over 1 minus x plus 1 plus x square in the denominator will have bx plus c in the numerator. Yes, this is what I'll have. Is that okay? Yes. What else? A upon 1 minus x is okay, plus bx plus c upon 1 plus x square is okay. We are supposed to find the values of a, b and c, and how do we find those values? We can compare the numerators. This numerator 2 is equal to a times, you take the LCM over here, this will be 1 plus x square and plus bx plus c, along with that you will have 1 minus x. And now you can compare the coefficients. Compare the coefficients of x square, x and constant to get the values of a, b and c. So compare. We compare, and what do we have? Coefficient of x square is a, and here the coefficient of x square is bx minus 1. Bx minus x will be minus bx square. So a minus b is the coefficient which is equal to 0 over there. Is that okay? Yes. The coefficient of x is bx minus cx. So it is b minus c times x. There is no x over here, and there the coefficient of x is simply 0. On the right hand side, the constant term is a, and you have plus c over here, which is equal to 2 over there, right? This is what you have. Okay, seeing these three equations, what I observe is, okay, these can be added to eliminate b. So what I'll get is a minus c is equal to 0. Using a plus c equal to 2, with this equation, what do we get? So 2a will be equal to 2, and a will be equal to 1. C will be equal to 1 because a is equal to c, and b is also equal to c. So b will be equal to 1 as well, right? That's what you get from this complete solution. So the partial fractions, therefore integral I will be equal to what? That was 2 upon 1 minus x times 1 plus x square, and from here what do I get? This integral will be further equal to a upon 1 minus x. What is a? This is 1 upon 1 minus x plus bx plus c. b and c are also 1. This is x plus 1 upon x square plus 1 dx. This is what you get. Is that okay? Yes, that's pretty simple. Okay, once you reach this stage, then what next? So next what you can do is, this can be integrated easily, right? Here this is a linear upon quadratic, so we'll have to apply concepts of linear upon quadratic over here, right? x1 upon x square plus 1 is not difficult. This x has to be converted into derivative of this particular x square plus 1 somehow, right? So the numerator has to be written as p times differential coefficient of denominator plus q, right? So derivative of this particular expression is nothing but 2x, right? So we'll have to convert this x into 2x. We'll do that. 1 upon 1 minus x plus, what is this? Half of 2x is what I get upon x square plus 1. Okay, that's simple x. And that third term, 1 upon x square plus 1 dx, that can be kept separate, right? This can be separated. This is what I'll get. Is that okay? Yes. What else? 1 upon 1 minus x, the integral will be equal to what? Okay, so the integral will be equal to, you can take a minus common from here and you can say, okay, this is a minus 1 upon x minus 1. The integral will be minus log mod x minus 1, or you can say, okay, it is log of modulus 1 minus x, and you have to divide with the coefficient of x, which is minus 1 over here. See, this is a linear function of x. Yes, this is what you'll do. Plus half is okay. Okay, and this becomes x square plus 1. If you substitute as t, 2x dx will be equal to dt. So this is dt upon t. The integral will be log modulus t, which is x square plus 1. And what about this? This is simply tan inverse x plus constant. That's what you'll have. 1 upon x square plus 1, the integral is tan inverse x. Yes. This whole thing simplifies to minus log modulus 1 minus x plus 1 by 2 log modulus x square plus 1 plus tan inverse x, right? These are the terms, and there will be a constant of integration over here, right? This is what you'll have. Minus log modulus of 1 minus x, this could be written as modulus x minus 1 as well, plus half log modulus x square plus 1 plus tan inverse x plus constant. That's the answer for this particular question, as you can see over here, right? In the 14th question, we have linear upon x plus 2, the x minus 1 upon x plus 2 whole square, right? How do we integrate this? So integration will not be difficult, right? This 3x minus 1 upon x plus 2 square can be simplified with the help of conversion into partial fractions. And what will be the partial fractions? A upon x plus 2 is one of the terms, plus b upon x plus 2 square is what you'll get, right? That is the partial fraction that you'll get. By the way, this kind of question can be solved using a very easy approach. And what is that? You can write 3x minus 1, try to write 3x minus 1 as x plus 2, right? Try to convert this into x plus 2. So 3 times x plus 2 is what I get. Okay, 3x is taken care of, plus 6, and we have to go up till minus 1, so this will be minus 7, right? If you write this in the numerator and you have x plus 2 square in the denominator, do you observe that this is the form that you are looking for in partial fractions? Yes, this x plus 2 gets cancelled with this, so you get 3 upon x plus 2 and minus 7 upon x plus 2 whole square. This is what you are looking at, right? So if there is only x plus 2 whole square in the denominator, there is a linear term in the numerator, then you can follow this kind of approach, which will be very, very simple. Yes, yes. What else? So we can use that kind of approach in general. Competitive exams allow us to use that kind of thing, but here we'll have to use the general method. And what is that? Let's write the numerator and compare the numerators. A times x plus 2 plus b is what I get, right? And comparing the coefficient of x, 3 is equal to a. Comparing the constant term, minus 1 is equal to 2a plus b. This is what you'll get, and that tells me b is equal to minus 1 minus 6, which is minus 7. Is that okay? Yes, b is equal to minus 7, a is equal to this. Okay, what else? So in the 14th question, we have 3x minus 1 upon x plus 2 whole square, and we have converted them into partial fractions. Therefore, integral I will be equal to integral of 3 upon x plus 2 and b is minus 7, so minus 7 upon x plus 2 square with respect to x. This is what we are supposed to integrate. 1 upon x plus 2, the integral is very simple. This is 3 times log of modulus x plus 2. Okay, minus 7 is okay. 1 upon x plus 2 whole square is similar to 1 upon x square, right? So 1 upon x square, the integral will be equal to minus 1 upon x. That becomes minus 1 upon x. This is what you get, right? Plus constant, and yes, that is my required answer for this particular question over here. As you can see, you could have moved in this direction and then directly here as well. That is also okay. But this is the approach that will follow for the board examination. The NCERT people love this, right? That's all in this question. In the 15th question, we have 1 upon x power 4 minus 1. Okay, this is again supposed to be solved with, since this is a rational function, we'll use partial fractions. So we'll have to factorize the denominator first of all. Let's do it. Let's factorize the denominator. This x power 4 minus 1 can be factorized as this. X square plus 1 times x square minus 1. Since x power 4 is nothing but square of x square, right? And this further, this x square plus 1 cannot be factorized further. But this x square minus 1 can be written as x plus 1 times x minus 1. Right? This is what you can follow. Is that okay? Yes. That looks simple. Okay. So a similar thing, once again, when we have to write this as partial fractions. So 1 upon x square plus 1, x plus 1, x minus 1. This whole expression will be equal to what? This whole expression will be equal to, this quadratic will have ax plus b in the numerator, x square plus 1 in the denominator. Yes. Then you will have this x plus 1 in the denominator, which will have a simple constant c in the numerator. Then you will have x minus 1 in the denominator, a simple constant d in the numerator. That's what you will be looking at. Right? Okay. Once you have written this, then we can find the values of a, b, c and d by comparing the numerators, right? So therefore, numerator 1 is equal to what? So ax plus b, if we take the LCM, will be the product of these two, which is x square minus 1 plus c times what you'll get. Please observe for c, x square plus 1 times x minus 1 will come. X square plus 1, x minus 1 plus d will have x square plus 1 times x plus 1. If you observe this carefully, this is what you'll get, right? Taking the LCM over here, numerator will be this, and here the numerator is simply 1. And now we will compare. There are 4 unknowns over here, yes? And you observe ax times x square will give me ax power 3, right? So first coefficient that we'll be looking forward to is coefficient of x power 3, which is 0 over here. 0 is equal to ax cube, which is a, and we have cx cube dx cube. So a plus c plus d is what I get over here. Is that okay? Yes. What else? Coefficient of x square. So let's focus on coefficient of x square, which is a 0 over here, will be equal to what? Coefficient of x square will be bx square. Yes. Is that all? Yes, that's what you'll get. There will be 4 terms. One will be x cube, the other will be bx square minus ax minus b, right? That's okay. So bx square is what I'll get. Here, cx square into this minus 1. So minus cx square was what I'll get. And will there be any other term of x square? Please observe. X power 3 minus x square plus x 9. That's the only term. And here also you'll get plus d. This is what you'll get, right? B minus c plus d as 0. What about coefficient of x? For coefficient of x, let's focus over here. This will be minus ax. And is there any other term? No, this is minus ax, right? So minus ax, that will be the coefficient of x. And here you'll have plus x into c. So plus c is what you'll have. There you'll have plus d, right? Is that okay? Yes. What else? Constant term which is 1 will be equal to what? Here you'll have minus b as the constant. There you'll have minus c as the constant, and there you'll have plus d as the constant, right? This is what you'll have. Is that okay? Yes, that's okay. That looks okay. So what next? What next? Do you see that we can easily find c plus, we can eliminate from the first and third equation, we can eliminate a easily. From these two equations, we can eliminate b easily, and we'll get two relations between c and d. Yes. So let's use them. Adding these two will give me c plus d is equal to 0. And these two will give me b minus b gets cancelled, minus c minus d. And this actually becomes 2c plus 2d equal to 0, which is similar as same as c plus d equal to 0. This becomes minus 2c minus 2d is equal to 1. So that becomes minus c plus d is equal to 1 by 2. Okay. And adding these two together will give me 2d is equal to 1 by 2 or d is equal to 1 by 4. C, which is equal to minus of d, will be equal to minus 1 by 4. Once you have found c and d, do you observe that c plus d is equal to 0. So therefore a will also be 0 from the first equation, this one, right? And use this to get the value of b. B is equal to c minus d, this minus this. So minus 1 by 4 will be minus 2 by 4, which is minus 1 by 2. So b is minus 1 by 2. This is what I'll be getting. That's the complete conversion into partial fractions. That's what you get. So a, b, c and d have been found. Therefore integral I, which was integral of that, therefore this, and therefore this whole expression could be written as integral of ax plus b, which is 0 times x plus b, which is minus 1 by 2 upon x square plus 1. Then you have c upon x plus 1, which is minus 1 by 4 upon x plus 1 plus d, which is 1 by 4 over x minus 1 dx. This is what you have. Is that okay? Yes. What else? Once we have this particular thing clearly mentioned, then this integral is not difficult to find. 1 upon x square plus 1 will have integral as tan inverse x minus 1 by 4 log modulus x plus 1 plus 1 by 4 log modulus x minus 1 plus constant term, and yes, that's what you get, right? That's the final answer for this particular question, as you can see over here. In the 16th question, we have 1 upon x times x power n plus 1. And how do we solve this? So, this solution of this can be found with the simple idea, and there's a one particular hint also given over here. Multiply numerator and denominator by x power n minus 1 and put x power n equals to t. So, that's something which you can do very easily, right? So, let's use that idea. I is equal to integral of 1 upon x times x power n plus 1 dx. This is what you have, right or not? Yes. So what do? We can multiply with x power n minus 1 and put x power n equals to t. Yes. So let's do it. Integral will be x power n minus 1 upon x power n minus 1 times x will be x power n. This is x power n plus 1 already there. This is dx. Is that okay? Yes. And we can put x power n is equal to t, and that tells me that n x power n minus 1 times dx will be equal to dt. This is what you can note, right? This is x power n minus 1. Dx will be equal to dt, and x power n minus 1 dx will be equal to dt upon n. So therefore, I will be equal to integral of x power n minus 1 dx, which will be equal to 1 by n dt upon, this becomes t times t plus 1. This is what you get. Is that okay? Yes. And this can further be broken down into two partial fractions. I'll write those two partial fractions. What is that? What I'll get is 1 upon t minus 1 upon t plus 1. You can convert into partial fractions very easily. You know the approach, right? So this is t plus 1 minus t, which is 1 upon t times t plus 1 is what I'll get. Conversion into partial fractions, so it's not difficult, right? And the integral will be 1 by n log 1 by n actually, not 1 by 2. This is 1 by n. In the bracket, you'll have log modulus t minus log modulus t plus 1 plus constant. And what is that? 1 by n log modulus t over t plus 1 is what I get, plus constant. Is that okay? Yes. T can further be replaced with x power n over there. 1 by n is okay. This is log modulus x power n over x power n plus 1 plus constant, and that is the final answer for this particular question. But is this the only approach? No, there's one more approach. Let's take a look at another approach over here. Let's take a look at alternative approach over here. And what is that approach? Tell me. Okay, I want to integrate this 1 upon x times x power n plus 1 integral with respect to x. So one simple approach would be, can you take this x power n common from here? Okay, what do we want to do? So I want to take this x power n common from here, and what does that give me? This is dx, which is okay. X power n common will tell me, okay, this becomes x power n plus 1, and this here is 1 plus 1 upon x power n. This is what you get. Is that okay? Yes, there was a 1 over there, so taking x power n common will give me this particular form. Is that okay? Yes. And now I can use a simple substitution. Much simpler than this whole process will be to use the substitution. Let 1 plus 1 upon x power n, this complicated expression, equals t in the denominator, and what does that give me? So this 1 derivative 0, x power minus n, the derivative will be minus 1 n upon x power n plus 1 dx will be equal to dt. This is the substitution, and therefore I will now convert to what? I will convert to dx upon x power n plus 1. Do you observe that the derivative has been created? Over there, derivative is present. So dt upon minus n, or minus 1 by n integral dt upon, this goes 1 plus 1 upon x power n is this t over here. This is what you get, right? And yes, this is minus 1 by n log modulus t, yes, plus constant. That is my final answer, except for the fact that we have to substitute the value of t over here. This is minus 1 by n log modulus t. T is this 1 plus 1 upon x power n plus constant, and that is my required answer for this particular question. So answer has been found in two different ways, but the answer should be same, right? Let's take a look at this answer over here. This is equal to this. Is this also equal to this? Yes, this is x power n plus 1 upon x power n, right? Okay, you take a reciprocal, you get a minus outside, right? Log of 1 by x is minus log x, right? So x power n plus 1 will come in the denominator, x power n will go in the numerator, taking the reciprocal, and there will be extra minus, which will be equal to this, right? That is the final answer for this particular question, as you can see, using the two methods over here. Now this is a simpler substitution, and this is using the idea of partial fractions that we have been seeing in this exercise. We have used partial fractions in between over here. This is simple substitution, and we have only used substitution in this particular method. So such questions will be easier with the help of this approach, as we have discussed over here. You can take a look at this, I'll get a side, and that's a complete solution of this 16th question, as you have seen. In the 17th question, we have cos x over 1 minus sin x times 2 minus sin x, and there's a hint also given over there. Yes. So what you can do is I is equal to integral of cos x over 1 minus sin x 2 minus sin x dx, and we can put sin x equals t. Sin x equals to t implies cos x dx will be equal to dt. This is what we'll have. Okay, sin x equals to t implies cos x dx will be equal to dt, and therefore I will be converted to integral of cos x dx is equal to dt over 1 minus t 2 minus t. This is what you have. Is that okay? I will be equal to integral of dt upon 1 minus t times 2 minus t. Okay, once you reach this stage, then you can use partial fractions, right? The idea of partial fractions to further simplify this and then integrate this. So the next step that will require is 1 upon 1 minus t 2 minus t will be equal to a upon 1 minus t plus b upon 2 minus t. So a will be 1 and b will be minus 1 over here. That's what you can find easily. One of the approaches is you multiply with 1 minus t, substitute t is equal to 1. So a will be equal to 1, b here will be equal to minus 1. This is what we'll get. These are the values of a and b. Oh, have you found those values using shortcut approach? No, I've just, yes actually, but you can, with so much amount of practice, obviously you can get a and b easily, right? So you could compare the numerators, 1 equal to a times 2 minus t, b times 1 minus t, and then you can compare coefficients to get the values of a and b. This is what you'll get. Okay, therefore integral I will be equal to integral I will be this, which is a 1 upon 1 minus t minus 1 upon 2 minus t dt. This is the integral that I will be getting, right? Yes, this is what I will be getting, and this can be integrated as log of modulus 1 minus t, just that I'll have to divide with this minus 1, which is the coefficient of t over here. This is a linear polynomial, minus log of modulus 2 minus t, again I have to divide with this minus 1 over here plus a constant term. This is my final answer, right? Oh, these two logs could be combined. Yes, this is log plus log of this minus log of this. So this becomes plus, will come in the numerator, 2 minus t upon 1 minus t plus constant, and this further is equal to log modulus 2 minus t. T was equal to sin x. So leave the answer in terms of x plus constant, and yes, that is the required answer for this particular question. 2 minus sin x upon 1 minus sin x in the modulus with log. That's a complete solution of this 17th question. In the 18th question, we have x square plus 1, x square plus 2 in the numerator. Then you have x square plus 3, x square plus 4 in the denominator. Now, how do we handle this? Okay, so the degree of numerator and degree of denominator, if you can clearly observe, the degree of numerator and degree of denominator are exactly same, right? So we'll have to divide first, yes. And everything is being dealt in terms of x square over here, yes. So can I simply use, I'm not substituting, mind you, I'm not substituting, just to simplify the expression, the look of the expression. Can I, for the time being, can I replace x square by maybe y, let's say, yes. So I'm not substituting, mind you, but let x square is equal to y. And now this complete expression becomes y plus 1 times y plus 2 over y plus 3 y plus 4. Yes or no? Yes. So this is y square plus 3y plus 2 over y square plus 7y plus 12. Yes or no? Yes. So I can divide this by this. Okay, dividing this will imply that I'll have to create this factor over there. So y square plus 7y plus 12 and minus what you'll get is, for getting 3y you'll have to subtract 4y from here, and for getting 2 you'll have to subtract 10 from here, upon y square plus 7y plus 12. This is what you get. Is that okay? Yes. So this will further simplify into what? This will further simplify into this divided by this is 1, which is okay, and minus can be taken out from here. This becomes 4y plus 10 over y plus 3 y plus 4 in the denominator. This is what you have in the denominator, right or not? Yes. So this 1 is very easy to integrate. 1 will be actually 1 only, right? Instead of y, you can replace x square. So this will be 4x square plus 10, x square plus 3, x square plus 4. But then again, we'll have to convert this into partial fractions, right or not? Yes. So for converting this into partial fractions, let's do it here only. And this 4y plus 10 upon y plus 3 y plus 4 can be taken as a upon y plus 3 plus b upon y plus 4, where values of a and b can be found easily by comparing the numerators, right? A times y plus 4, b times y plus 3. So a plus b will be equal to 4. That's the equation that you'll get. 4a plus 3b will be equal to 10. That's the other equation that you'll get, right? And using those two equations, we'll get the value of a as, remove this, substitute y is equal to minus 3, right? So 4 minus 3 is 1. Minus 12 plus 10 is minus 2. So a will be simply equal to minus 2 and b here will be equal to what? Put y is equal to minus 4. This becomes minus 16 plus 10, which is minus 6. This is not required. This is minus 1. Minus 6 upon minus 1 is simply 6. This is what you get. This is what you'll get, right? You check as well. This is minus 2y plus 6y is 4y. Minus 8 plus 18 is 10 over here. So a and b have been obtained, and therefore integration will not be difficult now, right? So I'll replace y again with x square, and therefore I will be equal to what? I will be equal to integral of that whole expression which is equal to this, and therefore 1 minus this. And this further is equal to this whole expression. What is that? 1 minus a upon y plus 3, which is minus 2 upon y plus 3, which is x square plus 3, right? I haven't used substitution, mind you, right? Here I have just replaced x square with y to simplify the look of the expression. That's all. Nothing more than that, right? This is 1 minus this, then you have minus b. B is 6 upon x square plus 4. That's what you get. dx. This is the integral that we are looking forward to. And this is x square plus a square, right, in the denominator. This is root 3 square. This is x square plus a square in the denominator over here. And what's the integral of 1 upon x square plus a square? So 1 upon x square plus a square is equal to 1 upon a tan inverse x by a. That is it. And yes, integral of 1 will be x. This becomes plus 2 by 1 by a is root 3 tan inverse x by a, which is root 3. What is this? Minus 6 by 2, 1 by a tan inverse x by a plus constant, and that is the required answer for this particular question. X plus 2 by root 3 tan inverse x by root 3 minus this is actually 3 tan inverse, this can be written as 3 tan inverse x by 2 plus constant. That's the complete solution. You can see the steps one by one. We have simplified the expression first, and at the end the integration is not difficult at all, right? So simplification, yes, that's a bit complicated, but other than that, finding the integrals, the integral part is very simple over here, right? That's the complete solution of this 18th question. In the 19th question, we have 2x upon x square plus 1 times x square plus 3. Okay, so there are x square as well as x terms. Okay, and since that's the case, so one of the approaches is to use partial fractions directly without thinking too much. But if you slightly observe this closely, you see that x square, the derivative is present in the numerator, right or not? Yes. In few question back, you had sin x in the denominator and cos x in the numerator, right? What did you do? You used a substitution, right? So if the derivative of this expression throughout is present over here, that will help us, right or not? Yes. So I is equal to integral of 2x upon x square plus 1 x square plus 3 dx. So instead of directly converted into partial fractions, although this could be converted into partial fractions, but that will be long. So what you can do is you can use substitution. X square is equal to t. Now this is a substitution, right? That makes it 2x dx is equal to dt. Therefore I will be equal to integral of 2x dx is dt upon x square plus 1, which is t plus 1, x square plus 3, which is t plus 3. This is what you have. Is that okay? Yes, that is okay. And once we have reached this stage, then dt upon t plus 1 times t plus 3 is what I have, and now I can convert these into partial fractions. Yes, yes. So let's do it. 1 upon t plus 1 times t plus 3 will be equal to a times t, a upon t plus 1 plus b upon t plus 3. And values of a and b can be found by comparing the numerators, right? Coefficient of x and constant term, right? The value of a therefore obtained will be equal to 1 upon 2. The value of b that will obtain will be equal to minus 3 plus 1, 1 upon minus or minus 1 upon 2. These would be the values of a and b, right? You can find those values easily. And I've told you the approach also, the shortcut approach would be that you multiply this t plus 1 throughout this and substitute t is equal to minus 1. Substitute t is equal to minus 1. This becomes a 0. And this will become 1 upon minus 1 plus 3. Minus 1 plus 3 will be 1 upon 2. Similarly, for b, you multiply by t plus 3 and substitute t is equal to minus 3. So this goes away, 1 upon minus 3 plus 1, which is 1 upon minus 2. That becomes this. And that's the value of b directly. Right. So therefore, I will be equal to this, which is equal to this, 1 by 2 times integral of dx upon dt upon t plus 1, okay, minus 1 by 2, that is b, integral dt upon t plus 3 is what I obtain. This is what you have. Integral of 1 by 2 times this is very simple. This is log modulus t plus 1 minus half log modulus t plus 3 plus a constant of integration. And you can combine these two logs. 1 by 2 will come out common. Log of modulus t plus 1 upon t plus 3 is what I get, plus a constant term. This is what I have. What about this expression 1 upon 2? This t can further be replaced by x square. So this is x square plus 1 upon x square plus 3 in the modulus plus constant term, and that is the required answer for this particular question, as you can see over here. Question number 28 says 1 upon x times x power 4 minus 1, and if you observe, okay, this is a polynomial in the denominator, there's no doubt about that. But if you go about finding the partial fractions directly, you'll face a lot of difficulty. So remember a previous question which we just saw some time back, 1 upon x times x power n plus 1. Do you see that this one is similar to this, right? And there were two methods which we approached this question was we approached this. One of the methods was given as a hint, and what did we do? We multiplied and divided by x power n minus 1, which is x power, this made it x power n minus 1 upon x power n times x power n plus 1. Then we used the substitution x power n is equal to t, and after that we used partial fractions. The other approach that we had over there was you take out x power n common from here, this makes it x power n plus 1. 1 plus 1 upon x power n is remaining over here, and you use this equal to t, this substitution over here. And you may recall the second method was pretty simple, as we saw in the question some questions back, right? So I can use approach similar to the second one over here. 1 upon x times x power 4 minus 1 dx, this is what I want to integrate, and yes, I can take out x power 4 common in the denominator. So this becomes x power 5. 1 minus 1 upon x power 4 is what I have over here with respect to x. This is what you want to integrate. And now the substitution that we're looking forward to is this. Let 1 minus 1 upon x power 4 is equal to t. So this derivative of 1 is 0, x power minus 4, the derivative will be minus 4, which is plus 4, it will become plus 4 upon x power 5 dx is equal to dt. And you observe that dx upon x power 5 is present over there in the integral, therefore I becomes equal to integral of dx upon x power 5 is 1 by 4 dt. So 1 by 4 comes over here, dt comes over here, and in the denominator this whole expression is equal to t. So the integral will become 1 by 4 log modulus t plus constant, or you can write it as 1 by 4 log modulus t. T is 1 minus 1 upon x power 4, which can be written as x power 4 minus 1 upon x power 4. This is the expression that you have, and plus constant, that is my required answer for this question over here. Okay. Using the other approach also you will get a similar answer, but I'm not solving that other approach. We have solved this question using this approach. I explained you the method of this, right? That's the final answer for this particular question over here. In the 21st question, we have 1 upon e power x minus 1, and how do we deal with this? There's a hint given over there that put e power x equal to t. So let's show it, yes. So I is equal to integral of dx over e power x minus 1, okay, and put e power x equal to t. What does that tell me? That the derivative of this e power x times dx will be equal to dt, okay. Therefore I will be equal to integral of dx, which is dt upon e power x, which is dt upon t actually, and e power x minus 1, which is t minus 1. Oh, this becomes 1 upon this polynomial, right? And now we can convert this into partial fractions, which is not difficult. This is 1 upon t, and you can write it as actually 1 upon t minus 1 minus 1 upon t. So t minus t plus 1. These will be the partial fractions. Oh, how did you do it orally? A simple question. T and t minus 1 will get cancelled in the numerator, right? So in the numerator, I have written t minus 1 over here. So this, what I have done is 1 upon t times t minus 1 can be factorized, can be converted into partial fraction by using this simple idea. One can be done as this. In terms of two factors of the denominator, this becomes 1 upon t minus 1 minus 1 upon t. And that's what I have written over there, right? So partial fractions using common sense. You can say common sense, right? This is what I have done. Oh, but we want to use the method. You can use the method. That's not an issue. So 1 upon t times t minus 1 can be written as a upon t, b upon t minus 1. You can get the values of a and b by comparing the coefficients of numerator, right? Let's see. This becomes log modulus t minus 1 minus log modulus t plus constant, which is actually equal to log modulus this upon this, and t can further be replaced as e power x minus 1, e power x. T is e power x, therefore t minus 1 will become e power x minus 1, t will become e power x plus constant, and that is the required answer for this particular question, as you can see over here. This is 21st question. 22nd question says integrate x dx upon x minus 1, x minus 2. And how do we do that? Okay, so once again, this is linear upon quadratic. Basically, you can use ideas of linear upon quadratic, or this can be handled with polynomial upon polynomial. Being a rational function, this can be handled with partial fractions. Which of these approaches will be simple? Partial fractions here will be very simple, right? So let's see the solution of this 22nd question over here. Okay, there were some options given over there. Yes, we can come back to those options whenever we want. Let's see. The first step that we want to apply is x upon x minus 1 times x minus 2 is equal to what? This is equal to a upon x minus 1 plus b upon x minus 2. This is what we have, right? Okay, and what will be the values of a and b? A can be found easily by putting x equal to 1 after removing this over here, 1 upon 1 minus 2, which is minus 1. B will be x equal to 2 after removing this, 2 upon 2 minus 1, which will be 2. This is what you have, right? So I, that is integral I, will be equal to integral of this whole expression, which is this, minus 1 upon x minus 1 plus 2 upon x minus 2 dx is what I obtain over here. Yes, this is what I have, and this is minus log modulus x plus 1 plus 2 times log modulus x plus 2 plus constant. Okay, this 2 will go in the numerator, plus log of this minus log of this will tell me log of x plus 2 square plus, and this will be in minus, this will come in the denominator, and there will be a modulus plus constant. This is what you'll get. That is my final answer for this particular question. Which of these options is correct? This is x plus, oh, this was x minus 2, not x plus 2. This was x minus 1, this is x minus 1, this was x minus 2, this is x minus 2, x minus 2 and x minus 1, right? That's what we have. And log of x minus 2 whole square, x minus 1 modulus. The correct option is option B, as you can see over here. This is the correct answer for this particular question using this approach. As you can see, the complete solution over here. Is that all? Yes. 23rd question says integrate dx upon x times x square plus 1, and there are some options given over here. One, this is multiple choice question. So how do we handle this? Dx upon x times x square plus 1. So the approach that you can follow over here is, there are various approaches. One of the approaches is that you can take this x square common from here. Okay, this becomes x cubed. This is 1 plus 1 upon x square, and you can use substitution 1 upon 1 plus x square, 1 plus 1 upon x square equal to t. That's one of the approaches. Other approach could be to use partial fractions directly, and let's use that. 1 upon, so what do we have over here is 1 upon x times x square plus 1 can be written as a upon x plus bx plus c upon x square plus 1. Yes, this is what you'll have. And the value of x will be nothing but, a can be found easily. You multiply with x and substitute x equal to 0, a will be equal to 1 upon 0 plus 1, which is 1. And bx plus c will have to be found separately. For that, we'll compare the numerators. 1 equal to a times x square plus 1 plus bx plus c times this will be bx square plus cx. Okay, comparing the coefficients of x square, you'll get a plus b, ax square plus bx square equal to this 0x square. Comparing coefficient of x, c, x will be equal to 0, and comparing the constant term, a will be equal to 1. A equal to 1 has been already found, that's not an issue. From here I can say that b is equal to minus 1 and c will be 0, as you can clearly see over here. Therefore, the integral I becomes equal to integral of this whole expression, which is further a upon x, which is 1 upon x, bx plus c, which is minus x, and that's gone. This is minus x upon x square plus 1 and dx. Is that okay? Yes. So we need the derivative of this in the numerator, and derivative of this is 2x. Okay, you multiply with the 2, divide by the 2. That's simple, yes. So integral of 1 by x is log mod x. Half is okay. This is derivative of this. This becomes dt upon t. The integral will be log mod t plus constant. This is what you'll get, right? So log mod x is the first term. First term log mod x. A and b seem correct. and then you have minus half log x square plus 1. Modulus of x square plus 1 is same as x square plus 1 because x square plus 1 is a greater than 0 quantity, right? Greater than 0, right? So this becomes minus half. So the correct answer for this particular question is this option A. That is the correct answer for this 23rd question, as you can see over here. That's the correct answer for this question. With this, we come to the conclusion of this exercise 7.5 from the chapter Integrals. In the next session, we'll talk about some more questions from the next exercise. Till then, all the best.